Are you ready?
Is this on?
If it's green, then it should be.
It's on, yeah.
Okay.
So 10 minutes.
Yes. Hi, everyone. My name is John, and this is my team member, Bowen, Mike, and Dylan. We are here to present to you our own tweet encoder, TweetVec. And the motivation for our project is actually we would like to group similar tweets together. For example, in the Russian plain case, we would like to see how these tweets are turned into our vector space, and I would like to see them closely linked together. So Bowen will walk you through the introduction, and I'll come back later. Yeah.
So the idea of vector space representations of textual data is not new. And like recently in 2013, Google came out with this technique called word2vec, which has become really popular. The basic idea here is to represent words as vectors and then learn these vectors as part of a backpropagation task. And the interesting part is that they took an unsupervised corpus of just textual data and created a supervised problem by formulating the task as, given the current word, predict the words which are in a window around it. And when they train on this task, they found really interesting results. So a small snippet of that space is presented here. So all the words corresponding to leadership ended up together, and similarly all numbers ended up together. These word embeddings found lots of applications in the NLP community for various tasks. One important thing to note here is that their model depends very heavily on the vocabulary size at training time. So the vocabulary size is the number of words in the training set, and as that increases, the model complexity also increases. After that, there was a whole bunch of research on embedding textual data into vector spaces. So there was paragraph to vec, context to vec, topic to vec. More recently, there was some work on encoding full sentences into vector spaces. But all of these tasks share this component that you first have to take words, represent them as vectors, formulate a learning task, and then learn those vectors for that task. In our work, what we want to do is we want to embed whole tweets into a vector space. And we could, so we basically want that tweets which are talking about the same kind of stuff to end up close in that vector space. And we could use any of the methods that I just described to you. But the problem there is that tweets are very noisy, and word embedding methods suffer from limitations such as they cannot generalize to unseen words. So my vocabulary size is fixed at training time, and when we move if we have a new word in the test set, then word embedding methods cannot deal with that. The other problem is that they make no assumptions about morphological regularity between words. So as human beings, we know that if we see the word pit, we know it's somehow connected to Pittsburgh because they're spelled similarly. And similarly for no matter how many O's I put in front of that, we all will get the meaning. But word embedding methods treat all words as completely independent units, and they cannot model similarities between the words based on their morphology. So one simple solution is to just increase the vocabulary size V at training time to include all forms of all words. But that is not a good idea because increasing vocabulary size leads to too many parameters and increases the model complexity. So instead, in our work, what we do is we actually model tweets starting from the characters as the basic unit, because the number of characters in any given language is fixed and usually very small. But we can't simply replace words in word2vec with characters, because the basic assumption in word2vec that given a word, predict the context around it. For characters, that's not a good idea because the same character might appear in millions and millions of different contexts, and the learning problem would not be very interesting. So what we actually did was to use a compositional model starting from characters, and the way we formulated our task as a supervised task was to use hashtags, because tweets come with hashtags, and they provide some sort of weak supervision. So John will talk more about that.
Yes, I will take care of the methodology. So in our methodologies, think about it intuitively. We would like to combine our text space and our tweet space, and even effectively group the tweets with the same hashtag together. And so mathematically, we would like to capture this as a minimization problem. We would like to minimize the hinge loss. So in this case, the E here represents our embedding for each tweet. So the ET plus, this one represents the embedding for the same hashtag, and this is a different hashtag. So we would like to enforce that the distance between the tweets and tweets with the same hashtag as regard to the different hashtag will be at least separated by a margin of m. And so in this way, we are actually providing a weak supervision to an unsupervised dataset. So next step. So RNN, the power of RNN lies in the fact that it actually provides a memory state. So it provides a longer memory for the distributional semantics. So this is an example of encoding a hello in the character level. So our baseline model is actually quite simple. We use a bidirectional RNN, which in our case we use a GRU. So think of it as similar to LSTM. So we take a tweet in, we break it down into characters. For each character, we look it up through our lookup table. This is a matrix of dimension v times vector dimension. So basically, for every character, we will map it into a vector representation, and we pass it through a bidirectional GRU, and we will take the head and tail, and then pass it through our fully connected layer, and then to form our tweet embedding. So this is actually our baseline. The problem with this model is that our tweet length is very, very long. It is 145 characters. So imagine a bridge. It is a very long bridge with no support in the middle. So what this embedding does is actually attribute a lot of weights to the head and tail. This is not exactly what we want, because tweets that starts with a wow and ends with a smiley face will be grouped together independent of what is in between. That is not what we want. So we would like to have some additional meaning. So we actually provided a second layer, which is words. So treating the previous one as one unit, we are actually passing each of this unit as a hierarchical model. So for all the characters, we are passing it through this unit